So the last thing that we covered in chapter 5, in part 1 of chapter 5, is the equations regarding mixture of gases. So the first equation that's shown here is called Dalton's law of partial pressures, which basically states that the total pressure in a container containing a mixture of gases is equivalent to the sum of the individual partial pressures of all the gases that's inside the container. And then you can combine Dalton's law of partial pressure with the ideal gas law equation, which basically is equivalent to PV equals nRT, okay, where P equals pressure, V equals volume, N is the number of moles, R is the ideal gas constant, and T is temperature. And so you can combine these two equations and you can solve for the individual partial pressures of the gases. And so, for example, if you have PA, right, the partial pressure of gas A is equivalent to the number of moles of gas A times RT divided by V. So we can use the same, so the temperature here and the volume is basically the same because all these gases are contained in the same container. And so they share the same volume, they share the same temperature. The only difference is the number of gas molecules, right? The number of moles of these gases. And so, yes, we can combine Dalton's law of partial pressure along with ideal gas law equation, as shown here at the bottom. So let's look at this first example here as a recap before we move on to the next concept. A 1 liter mixture of helium, neon, and argon has a total pressure of 662 millimeter mercury at 298 Kelvin. If the partial pressure of helium is 341 millimeter mercury and the partial pressure of neon is 112 millimeter mercury, what mass of argon is present in the mixture? So the first thing that you want to do here is to write down what's given. Okay, so let's write down what's given. So here we have the total volume, and the total volume of the container, or the amount of gas, is 1 liter. And then we're also given the total pressure. The total pressure inside the container is 662 millimeter mercury. We're given the temperature, which is 298 kelvins. We're given the partial pressure of helium, which is 341 millimeter mercury. And the partial pressure of neon, which is equivalent to 112 millimeter mercury. And then it's asking for the total mass of argon. I guess we can calculate this in grams. Okay, so we can calculate the mass of argon in grams. So the first thing that you want to do here is to write down what's given and then try to analyze what is being asked. And so it's telling us that the container has 3 different gases: helium, neon, and argon. And you have the partial pressure of helium, you have the partial pressure of neon, and we don't have the partial pressure of argon. But that's something that we can calculate because we already have the total pressure. So we can calculate the partial pressure of argon. So this is something that we can calculate easily, right? Because according to Dalton's law of partial pressure, the total pressure is equivalent to the sum of the partial pressures. So partial pressure of helium plus partial pressure of neon plus the partial pressure of argon should equal 662 millimeter mercury. So we can go ahead and write that down. So we can easily calculate for the partial pressure of argon by subtracting the partial pressure of helium and neon from the total pressure. So in this case, we have partial pressure of argon is equivalent to total pressure minus the pressure of helium minus the pressure of neon. And so plugging in the numbers and calculating for the partial pressure of argon, we get 209 millimeter mercury. So it's basically 662 minus 341 minus 112 gives us 209 millimeter mercury. So now, how do we calculate the mass of argon? So if you remember, we can combine Dalton's law of partial pressure with the ideal gas law. And so what is the ideal gas law equation? Well, we know that PV equals nRT. Okay, where R is the ideal gas constant. Okay, so we know the pressure of argon, right? So we know this. We know the volume of the container. We know the total volume of the gas. We know what our constant is, and we know the temperature. It's given right here. And so what we can do is try to calculate the amount of moles of argon. So this is the moles of argon. Okay, so we can calculate for the number of moles of argon, and then from there calculate the mass of argon using the molar mass of this element. And so let's go ahead and do that. But before we plug in any numbers in this equation, we want to make sure that the units match. So remember that the value of R and the units of R is liters atmosphere per mole Kelvin, right? So those are the units for the ideal gas constant. It's liters atmospheres per mole Kelvin. So let's go ahead and write that down. So this is equivalent to 0.0821 liter atmosphere per mole Kelvin. All right, and so that means that we're going to have to convert millimeter mercury into atmosphere, and then everything else should already be with the correct units. So we can simply convert the pressure from millimeter mercury into atmosphere by dividing 209 by 760. Okay, so divide 209 by 760 gives us 0.275 atmospheres. So now we can isolate the number of moles of argon and solve for it. So here we've isolated the number of moles of argon, which is equivalent to the pressure of argon, partial pressure of argon times volume divided by RT, right? Ideal gas law times temperature. And then all you have to do now is plug in the numbers and making sure that the units match. So we have 0.275 atmosphere times 1 liter divided by 0.0821 liters atmospheres per mole Kelvin times 298 Kelvin. And then you can see that the units start canceling out. So you have atmosphere and liters up here, which will cancel with these two right here. And then kelvins will cancel out as well. And what's left is the number of moles. Okay, so you get number of moles of argon. So plugging in all the numbers into the calculator, we get the number of moles of argon, which is 0.0112 mole. And then we can convert moles of argon using the molar mass of argon. So all you have to do is multiply this by the molar mass of argon, which is 39.95 grams per mole. So we're going to multiply this by the moles of argon, 39.95 grams per mole. So you can see that the number of moles will cancel out. And what's left is the mass in grams. So 39.95 times 0.0112 gives us 0.449 grams. So 0.449 gram of argon. So that would be the answer to this problem. And here's a cleaner version. So again, the first step is to determine the partial pressure of argon, which gives us 209 millimeter mercury, and then convert it to atmosphere. And then you use ideal gas law, all right, combine it with the partial pressure to get the moles of argon, which is shown here. And then once you've determined the moles of argon, you convert that to mass of argon, which is 0.449 grams. So besides using the ideal gas law equation and partial pressure, there's actually another way to relate partial pressure with the total pressure. And this is using this concept known as mole fraction. So let's take a look at what mole fraction is and how we can relate partial pressure with the total pressure in terms of a mathematical equation. So here, if we take the ratio between the partial pressure of a single gas and the total pressure, PA, right, the partial pressure of gas A divided by the total pressure, what you get is the mole fraction. Because if you use the ideal gas law, right, and try to solve for PA, the partial pressure of gas A, that's equivalent to NA times RT divided by V. Okay, and we can do the same thing for the total pressure. It's the total number of moles times RT divided by V. And so because we're looking at the gases in terms of the fact that they're contained in the same container, they share the same temperature and they share the same volume. And so this basically cancel each other out. And what's left is a fraction of the moles, hence mole fraction. So Na, the fraction of, or the mole of A divided by the total number of moles is equivalent to the mole fraction. And they're given this a symbol, which is a Greek letter chi. So chi A is the mole fraction of A, which is essentially equivalent to this ratio between the moles of a single gas per the total number of moles of the gases in that container. Okay, and so the number of moles of a component in a mixture divided by the total number of moles in the mixture is basically the mole fraction, because everything else will cancel each other out. Okay, and so you can rearrange this equation, right? The ratio of the partial pressure and the total pressure is equivalent to the mole fraction. We can rearrange this equation so that this fraction is equal to chi A, mole fraction of A, times P total. So we're basically rearranging this. So let me write that down. So the partial pressure of A divided by the total pressure is essentially equivalent to the number of moles of A divided by the total number of moles. And we know that the total number of moles is essentially chi, the symbol chi A. And so we can rewrite this equation. So we can rewrite this as PA divided by P total equals chi A. And then we can rearrange this further so that we only have the partial pressure relative to the total pressure. So that would be PA equals chi A times the total pressure. So essentially, if we know the total pressure, okay, and we know the mole fraction of A relative to the total number of moles, then we can calculate the partial pressure of gas A. So let's take a look at an example here. It says a 12.5 liter scuba diving tank contains a helium-oxygen mixture known as heliox, made up of 24.2 grams helium and 4.32 grams of oxygen gas at a temperature of 298 kelvins. Calculate the mole fraction and partial pressure of each component in the mixture and the total pressure of the mixture. So the first thing you want to do here is to try to understand what's going on here, right? Try to understand and extract the information that you need in order to solve the problem. So let's go ahead and do that and extract the information that we need. So this is the information, all the information that we are able to extract out, right? We know the total volume of the container, it's 12.5 liters. We know the mass of helium, one of the gases, and oxygen, the other gas, 4.32 grams. We also know the temperature, which is 298 kelvins. What we're trying to find here is the mole fraction of helium and the mole fraction of oxygen gas, which is pretty easy to calculate. and then calculate the total pressure. So before we can determine the mole fractions, we need to convert masses of the gases, right, into number of moles. So convert moles of helium and moles of hydrogen. So here it shows you the number of moles of helium and the number of moles of oxygen gas. So I've already converted it for you. So all you have to do for mass of helium is to divide 24.2 by the molar mass of helium, which is 4 grams per mole. So 24.2 divided by 4 gives you 6.05 moles. And then for the moles of oxygen gas, 4.32 divided by the molar mass of oxygen gas, which is 32 grams per mole. So 4.32 divided by 32 gives us 0.135 mole. All right, so now we can calculate the mole fractions, right? We have the number of moles of helium, number of moles of oxygen. If we know the total number of moles, which we do, all we have to do is add the two numbers, then we can calculate chi, all right, the mole fraction. And so adding these two numbers up gives us 6.185 moles. So this is your N total. All right, so now that we have the individual number of moles and N total, we can calculate mole fractions. Okay, so for example, for chi helium, we know the moles of helium, which is 6.05, and we're going to divide that by the total, which is 6.185, and so the mole fraction for helium is 0.978. Okay, so this is basically chi helium. And then we can do the same thing for chi O2, which is 0.135 divided by 6.185. And this gives us 0.0218. So this is chi oxygen gas. So from here we can calculate P total, right? P total, or the total pressure, is equivalent to the pressure of helium plus the pressure of oxygen gas. So if we know the pressure of helium and oxygen gas, then we just add them together and get the total pressure. Is that something that we can calculate? Can we calculate the pressure of helium and the pressure of oxygen gas from the given information? And the answer is yes. We can use ideal gas law equation. PV equals nRT. Okay? We know the pressure of helium. We know the number of moles of helium right here. We know the ideal gas constant R. We know the total volume and the temperature. We can calculate the partial pressures using the ideal gas law. So here are the equations using the ideal gas law equation. So the pressure of helium is equivalent to the number of moles of helium times RT divided by V. So we have all these numbers. We have the moles of helium. We know what the ideal gas constant is. So let me just write that down. So R is equivalent to 0.0821 liter atmosphere per mole Kelvin. We know the temperature, which is 298. We also know the total volume, which is 12.5. So all you have to do now is plug in all the numbers, and we can get the partial pressure of helium. Here we get 11.8 atmosphere. So this is the partial pressure of helium, and we can do the same thing for oxygen gas. We know the number of moles of oxygen gas. We know ideal gas constant R. We know the temperature and volume. So plug in the numbers, and we get 0.264 atmosphere. So now we can add the two numbers 11.8 plus 0.264, and we get 12.1 atmosphere. atmosphere. So that would be the total pressure of the mixture. We know the chi values, partial pressure of helium, we know the partial pressure of oxygen gas, and we know the total pressure. There are other ways to calculate the total pressure because you know N total. So this is another way to calculate for P total. So P total equals N total times R times T divided by V. So when you do this, you get the same number, 12.1 atmosphere. Same thing. So here's a cleaner version. So we wrote down everything that was given and the things that we need to calculate. Right? So the first step is to basically convert the masses to moles of the gas, which we did. And then we calculated the total number of moles by adding the two numbers, which we also did. And then we took the fraction, right? So 6.05 divided by the total gives you the mole fraction for helium, and then the mole fraction for oxygen gas. And then step 3, we calculated the total pressure using P total equals N total times RT divided by V, which is equivalent to 12.1 atmosphere. Or you can also calculate the partial pressure just by simply multiplying the mole fraction by the total to get the partial pressure of each of the gases. So again, there's more than one way to solve the problem as shown here in different ways. So the next topic that I want to talk about here is this concept known as collecting gas over water. So sometimes you can measure the volume of any gas by displacement, water displacement. By collecting gas in a, let's say, graduated cylinder like this one shown here, we can measure the amount of gas that's produced by this specific chemical reaction here. So in this example, we have a zinc metal that's basically being dissolved in sulfuric acid. So if you remember, this is an example of a single displacement reaction in which you have a solid metal that's reacting with the acid, and so you're turning the solid metal into zinc ion. And in the process, you're generating hydrogen gas. And the hydrogen gas is collected over here in this graduated cylinder. But because this chemical reaction is in water, water vapor is also collected in this graduated cylinder because water evaporates even at low temperature. So it doesn't have to be at 100 degrees Celsius. Water can evaporate at lower temperature. It's just at a much slower rate, right? And so the gas that's collected is known as a wet gas because that gas that's collected also contains water vapor. So here's a slightly more sophisticated setup of this collection of gas via water displacement. So you have a chemical reaction that's happening in this tube right here. So you have a zinc metal that's dissolving in hydrochloric acid. And this chemical reaction produces hydrogen gas. And this hydrogen gas travels from the test tube into the collection flask, which is this beaker right here, this inverted beaker, right? And so you have the hydrogen gas that's being collected in this container, but it also contains water vapor, okay? And the reason why is because hydrochloric acid is dissolved in water. So it's a hydrogen chloride dissolved in water. And so what you get is hydrogen gas plus water vapor. And so because we have a mixture of gases here, right? You have, let's say, a hydrogen gas and water vapor. We can use Dalton's law of partial pressure to determine the pressure of the gas that was generated. Okay, so if you remember, Dalton's law of partial pressure is basically the total pressure of the gas inside is equivalent to the sum of the partial pressures of those gases. And so notice that this container is an open container. So what that tells you is that the pressure outside, which is basically the atmospheric pressure, is equivalent to the total pressure inside. Okay, so P total, or total pressure, is equivalent to the atmospheric pressure. So whenever you're collecting gas over water, you have two kinds of gases in the container. One is the water vapor, and the second one is the gas that you collected, right? The gas that's generated from the chemical reaction. And so in order to determine the pressure of the gas that was generated, you need two information. The first one is the total pressure, which is basically the atmospheric pressure, and the vapor pressure. And this vapor pressure is basically the pressure of the water vapor. Okay, so if you know the total pressure and the vapor pressure at a specific temperature, then we can determine the partial pressure of the gas that we just collected. And so here in chemistry, you'll be given a table that contains the vapor pressure of water at a specific temperature. Okay, so you don't have to experimentally determine that or remember those numbers. So you're going to be given a table, and all you have to do is know how to use that table to determine the pressure of the water vapor, hence the vapor pressure. And so vapor pressure is dependent upon temperature. So the higher the temperature, the higher the vapor pressure. So this is the table that will be provided on the test. So as you can see, you have the pressure of water vapor at specific temperatures. So at 0 degrees Celsius, the pressure is 4.58. And as you can see, as the temperature increases in degrees Celsius, so is the vapor pressure of water. Okay, so at 100 degrees Celsius, at boiling point, the pressure is 760 millimeter mercury, or 1 atmosphere. So again, if we know the vapor pressure of water at a specific temperature, then we can calculate the partial pressure of the other gas that's generated from the chemical reaction. So in this example, it would be the pressure of hydrogen gas. Okay, and so if you remember, again, Dalton's law of partial pressure, the total pressure is equivalent to the sum of the individual partial pressures. So let's look at an example here. So it tells you that you perform an experiment at a specific temperature and a specific atmospheric pressure. So the atmospheric pressure is measured to be 755 millimeter mercury. So this is basically equivalent to the total pressure. And the water temperature was set at 20 degrees Celsius. What is the pressure exerted by the hydrogen gas in the cylinder? So here you have this experiment going on, a chemical reaction between a zinc metal and sulfuric acid solution, and this generates hydrogen gas and water vapor. And so if we know the partial pressure or the vapor pressure of water at 20 degrees Celsius, then we can calculate the partial pressure of the hydrogen gas. So at 20 degrees Celsius, it's 17.5 millimeter mercury. So because we know the total pressure, 755 millimeter mercury, we can subtract 17.55 from 755, and what we get is the partial pressure of hydrogen gas. So here's Dalton's law of partial pressures. The the partial pressure of hydrogen gas plus the partial pressure of water, which is basically the vapor pressure, gives us the total pressure. And again, the total pressure is equal to the atmospheric pressure. And so to calculate the partial pressure of hydrogen gas, we can isolate this and subtract water, or the vapor pressure of water, from the total. So in that case, 755 minus 17.5 gives us 737.5 millimeter mercury. So let's look at this example here, which basically combines Dalton's law of partial pressure and all the other concepts that you've learned in this chapter. In order to determine the rate of photosynthesis, which is the conversion of carbon dioxide and water into glucose and oxygen gas, the oxygen gas emitted by an aquatic plant is collected over water at a temperature of 293 kelvins and a total pressure of 755.2 millimeter mercury. Over a specific time period, a total of 1.02 liters of gas is collected. What mass of oxygen gas in grams forms? And you're provided the table of the vapor pressure of water down here. So the first thing that you want to do here is to extract all the information that we need, right? And then analyze that information and find an approach to solve this problem. So here we're given the temperature at which the experiment was performed, right? We're given the temperature, which is 293 kelvins. And then we're also given the total pressure, which is basically the pressure of the atmosphere. So that's 755.2 millimeter mercury. We're given the volume of gas that was collected. And again, this gas collected will be a mixture of oxygen gas and water vapor, because it tells you that it was collected over water. And the volume, the total volume, is 1.02 liters. And then it's asking for the mass of oxygen gas that was released in grams. And so how do we approach this problem? Well, we need one other information here. Because this is collected, or because the oxygen gas was collected over water, it's going to be a mixture of oxygen gas and water vapor. So we will need the vapor pressure. At what temperature? Well, it tells you it's 293 kelvins. This is in Celsius. And so what we can do is convert 293 kelvins into degrees Celsius so that we can determine what the vapor pressure is for water. So now by converting 293 kelvins to degrees Celsius, we get 20 degrees Celsius. And we can look at the table right here, and you can see that the vapor pressure of water at 20 degrees Celsius is 17.55 millimeter mercury. So that's the other information that we will need in order to solve this problem. So this is the vapor pressure of water. So now we can solve for the pressure of the oxygen gas. So we can solve this pressure of oxygen gas by simply using this Dalton's law of partial pressure. All right, so we know the total pressure, we know the vapor pressure, we can find partial pressure of oxygen gas. So we can subtract 17.55 millimeter mercury from 755.2 millimeter mercury. So subtracting the vapor pressure of water from the total pressure gives us the pressure of oxygen gas, which in this case is 737.65 millimeter mercury. Now from here, we can determine the mass of oxygen gas by using ideal gas law, right? The ideal gas law equation is PV equals nRT. So if we know the number of moles of oxygen gas, we can convert that into grams of oxygen gas. So here's the equation, right? PV equals nRT. So we're going to use the pressure of oxygen gas, the total volume of the gas, which is 1.02, is equal to the number of moles of oxygen gas times R times T, where the temperature is 293 kelvins. So if we can isolate and solve for the number of moles of oxygen gas, you can convert that into the mass of oxygen gas. So let's go ahead and do that. So we know the value of R, which is ideal gas constant, and it's 0.08201 liters atmospheres per mole Kelvin. But the problem here is the pressure of oxygen gas. This needs to be converted to atmospheres first. So let's do that. All you have to do is divide 737.65 by 760. So here it is. So divide 737.65 by 760 basically converts millimeter mercury to atmosphere. So the answer is 0.971 atmosphere. So now we can plug in this number into this equation and then solve for the number of moles of oxygen gas. So isolating the number of moles of oxygen by itself gives us this equation here, right? So the pressure of oxygen gas times volume divided by RT, right? The ideal gas constant times temperature. So plugging in all the numbers, we get this. And into the calculator, we get 0.0412 mole of oxygen gas. But we're not being asked for the number of moles of oxygen gas. We're being asked for mass of oxygen gas. And so you can easily convert this to the number of moles of oxygen by multiplying this by the molar mass of oxygen gas, which is 32 grams per mole. So multiply this number by 32 grams per mole, the molar mass of oxygen gas, and this gives us 1.32 grams of oxygen that formed in this photosynthesis, this chemical reaction. And here's a cleaner version. Again, the first thing that you want to do is collect the information, extract the information from the problem. So the temperature converted to degrees Celsius, and then the first step is to calculate the partial pressure, knowing the total pressure and the vapor pressure of water, and then we converted it to atmosphere, and then we use the ideal gas law equation to determine the number of moles of oxygen gas, and then we converted the number of moles of oxygen gas into grams of oxygen gas, which in this case is 1.32 grams. So the last three things that I want to cover in this chapter are standard conditions, molar volume, and density of gases, and how that relates to the ideal gas law equation. So the first concept out of the three that I want to talk about is standard conditions. So the idea behind this is it makes comparison between measurements a lot easier and simpler, right? So let's imagine that you're comparing the heights of two mountains, right? Mount Everest and Mount Chimborazo. What would be the best way to compare the heights? Well, you want to measure the height with a standard condition, right? And sort of like a frame of reference. And in this case, it would be sea level. So every time you're making comparison regarding the height of any mountain in the world, you would use the reference sea level, right? So you say Mount Everest is 29,000 feet above sea level compared to 20,500 feet for Chimborazo. And so when it comes to gases, okay, the volume of a gas varies with pressure and temperature. So a set of conditions or standard must be followed in order to make comparison a lot easier in terms of measurements. And so we call these standard conditions. And for gases, it's called STP, which is short for standard temperature and pressure. And when it comes to pressure, the standard pressure is 1 atmosphere, okay, which is equivalent to 760 millimeter mercury. And the standard temperature has to be 273 kelvins, or basically 0 degrees Celsius. The second concept is called molar volume, and molar volume is related to the standard temperature and pressure, the standard conditions concept. The volume occupied by 1 mole of a substance, a gas, is its molar volume at standard temperature and pressure. So how do we prove this mathematically? How do we prove that the volume occupied by 1 mole of a gas is equivalent to its molar volume at standard temperature and pressure? So let's say that we, again, this is related to the ideal gas law and standard temperature and pressure. So let's say that the ideal gas law equation is PV equals nRT. And if we have 1 mole of a substance, and we have the pressure, which is 1 atmosphere, and we have temperature, which is 273 kelvins, and plug this into this equation shown here, the ideal gas law equation, and solve for volume, what do you get? Whatever it is, that is known as the molar volume. So let's try to plug in all the numbers here. So N volume is equal to nRT divided by pressure. So that's what volume is. Right? So we're going to plug in all the values. So we have 1 mole times the ideal gas law or the ideal gas constant times the temperature, which is 273 K, divided by pressure, which is 1 atmosphere. So plug this into the calculator, and what you get is what they call molar volume, which is always 22.4 liters. So at standard temperature and pressure, the volume of 1 mole of any gas is always going to be 22.4 liters. So here's a cleaner version of the calculation. You have nRT divided by P, 1 mole times the ideal gas constant times temperature or standard temperature divided by standard pressure. And you always get 22.4 liters. And again, the molar volume of any gas at standard temperature and pressure is always equal to 22.4 liters. So here's a few examples. If we have 1 mole of helium at standard temperature and pressure, the volume would be 22.4 liters. 1 mole of xenon, one of the other noble gases, at standard temperature and pressure would also be 22.4 liters. Methane gas at standard temperature and pressure, 1 mole of that gives 22.4 liters as well. So 1 mole of any gases has a molar volume of 22.4 liters. So if you have 2 moles of the gas, any gas, it would be double that value. So 2 times 22.4 would be 44.8 liters. If you have 3 moles, it would be triple that value, 67.2 liters, and so on. So the last concept that I want to talk about here is density of a gas. So in the previous chapters, you learned about density of liquids and solids and how to calculate the density. This time you're going to learn about density of gases. So just like any other density type of calculation, by definition, density is the ratio between the mass and volume. So it's mass divided by volume. The density of solids and liquids are typically measured in grams per milliliter, but in gases it's generally given in grams per liter. The mass of 1 mole of gas is known as the molar mass, and you learn about that. It's grams per mole. And the volume of 1 mole at standard temperature and pressure is always 22.4 liter. That's the molar volume. And so density, the equation for density for gases, is the molar mass divided by the molar volume, which is 22.4 liters. So now the question is, how would density change if the molar mass was increased? Okay, so as you can see based on this equation, that the molar mass is directly proportional to the density of the gas. So the higher the molar mass, the higher the density, right? So increasing the molar mass of the substance increases the density. Okay, so density increases or decreases with molar mass. They are directly related. You increase one, the density also increases. You decrease the molar mass, density also decreases. So an example is the density of helium and nitrogen gas. So you know that helium balloon can just easily float in air, whereas nitrogen balloon, they're heavy, right? So they don't really float on air. And so you can see that the density of helium is a lot lower compared to the density of nitrogen gas. And the reason why is because the molar mass of helium is lower than the molar mass of nitrogen gas. So when you plug in the numbers into the equation for density of gases, 4 grams per mole is the molar mass of helium divided by the molar volume gives us 0.179 grams per liter. Whereas for nitrogen gas, 28.02 divided by 22.4 gives us 1.25 grams per liter. And so quantitatively speaking, you can see that the helium gas is lower in density than nitrogen gas. So now using the ideal gas law equation, how do we prove that density is directly related to molar mass? How do we prove mathematically that density is directly proportional to the molar mass of the gas? Well, let's take a look. So we know the equation for ideal gas law, right? It's PV equals nRT. So how can we relate the density of the gas with this ideal gas law equation? How do we incorporate density, right? The equation for density in this gas law equation. So we know that density is basically mass divided by volume. Okay, so what if we divide and move volume to the right hand side? So we divide both sides by volume. So you can see how the units would cancel out, volume would cancel out here, and now you're left with pressure. So pressure equals nRT divided by volume. Another piece of information that we'll need is molar mass. We know that the molar mass of a gas is equivalent to grams per mole, right? So it's basically mass in grams per mole. Okay, so let's just say grams per mole. Grams per mole. And we know that the symbol for mass is M, and the symbol for moles is N, right? Number of moles. And so for this equation here, pressure is equivalent to number of moles times RT divided by V. What we can do is we can multiply both sides of the equal sign by the molar mass, right? So this is molar mass right here. So what happens if we do that? All right, so we're going to multiply both sides by molar mass, which is M over N. Okay, so this is molar mass. And so because we're multiplying this side by the molar mass, we can do the same thing on the right-hand side. So, but this time, I'm just going to leave it as MM for molar mass. All right, so as you can see here, the number of moles would actually cancel out, N, right? Number of moles. So this cancels out. And then notice mass divided by volume. That's density. And so we can replace this with density, because density is mass divided by volume. And so we can rearrange this equation. So now we have the molar mass times the pressure is equivalent to RT times density. Mass over volume is density times RT. So we can rearrange this. We can rearrange this equation in terms of density and molar mass by dividing both sides by RT. So divide both sides by RT. So RTs would cancel out, and we've now isolated density by itself. So in that case, density is equivalent to the molar mass of the gas times the pressure divided by RT. So now we have incorporated density into the ideal gas law equation. Okay, so again, you don't have to memorize or really know how to derive this equation here. You just have to remember that density is equivalent to this. So you have to remember this equation, but you don't have to really learn how to derive this equation. But it would help to remember the density equation if you knew how to derive it. So this equation basically shows you that as molar mass of gas increases, the density also increases. And if the molar mass decreases, then density also decreases. And here's a cleaner version of the derivation. So you can derive the equation using ideal gas law and the molar mass. And then the book uses this capital micro symbol for molar mass. So density is equivalent to pressure times the molar mass divided by RT. Here's an example of a problem involving density. Calculate the density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeter mercury. So the first thing that you want to do here is to extract out the information. So let's do that. So here we're given the density of nitrogen gas, which is equivalent to, so this is what we're trying to find. And we're given the temperature, which is 125 degrees Celsius. And you can convert this to kelvins by simply adding 273. So in that case, we have 398 kelvins. And then we're also given the pressure, which is 755 millimeter mercury. And here you need to convert this to atmosphere. And we can do that by simply dividing 755 by 760, which gives us 0.993 atmosphere. All right. So now there's one other thing that we can calculate, the molar mass of nitrogen gas. Right? So in order to determine density, we need the molar mass of the gas. So in this case, so capital micro sign, or the molar mass of nitrogen gas is equivalent to 28.02 grams per mole. So now we have all the information that we need. We also know what R is equivalent to. It's 0.0821 liters atmosphere per mole Kelvin. All right, so now we can plug this into the equation for density, which is basically pressure times the molar mass divided by RT. All right, we know the pressure, which is 0.993 0.93 times the molar mass, which is 28.02. And then we're going to divide this by the ideal gas constant times the temperature in kelvins, which in this case is 398 kelvins. All right, so plug this into the calculator. We get 0.852 grams per liter. All right, so that would be the density of nitrogen gas at this specific temperature and pressure. And here's a cleaner version of the calculation. So the first thing that you want to do is to extract all the information and then calculate the molar mass of nitrogen gas and then plug in all the information into this equation. So, but before you do so, you want to make sure that you convert to the proper units from millimeter mercury to atmosphere, or degrees Celsius to kelvins, and then plug in all the numbers and we get the same number here, 0.852 grams per liter. And here's one final example where you could determine the molar mass of a gas depending on the sample information. All right, so let's say we have a sample of gas that has a mass of 0.311 gram. Its volume is 0.255 or 0.225 liters at a temperature of 55 degrees Celsius and a pressure of 886 millimeter mercury. Find the molar mass. So again, the first thing that you want to do here is to extract out the information. So again, we're given the mass of the sample, which is equivalent to 0.311 gram. And we're also given the volume of the gas, which is 0.225 liter. And then the temperature as well. So temperature is equivalent to 55 degrees Celsius and the pressure at 886 millimeter mercury. So now we're being asked for the molar mass. So here you want to convert degrees Celsius to Kelvin first and millimeter mercury into atmosphere. So again, for temperature, add 273 and you get temperature in kelvins. So in this case, we have 328 kelvins. And then for pressure, just divide that number by 760 and we get 1.166. I'm just going to round this up to 1.17 atmosphere. So in this example, we can determine the molar mass. We can determine the molar mass of the gas by simply dividing the mass of the gas by the number of moles, because we know that number of moles, or the molar mass, is equivalent to grams per mole, right? So if we can divide this number by the number of moles of gas, then we can determine the molar mass of the gas. So we can actually use a normal ideal gas law equation to determine the number of moles of the gas. So in that case, we can use PV equals nRT and solve for the number of moles of the gas. So in that case, number of moles is equal to PV divided by RT. All right, so plug in the numbers. So N is equivalent to pressure, which is 1.17. multiply that by volume, which is also given, 0.225. So the volume here is supposed to be 0.225. All right, and then we're going to divide this whole thing by RT. And temperature is 328 kelvins. All right, plugging this into the calculator, and we get 0.00978 mole of the gas. So now that we have the mass of the sample, which is 0.311 gram, we can divide this by the calculated number of moles. And what we get is the molar mass. So 0.311 divided by the number of moles gives us 31.8 grams per mole. All right, and that would be the molar mass of the gas that was experimentally determined. And here's a cleaner version of the calculation. So again, the first thing you want to do is extract the information and then use this equation, because we know that molar mass is the mass per moles and the ideal gas law equation. So if you know the number of moles, plug that into this equation, because we're already given the mass, you get the molar mass. So you want to make sure that the units match up first. So convert millimeter mercury to atmosphere, degrees Celsius to kelvins, and then plug in the information, and we get the number of moles of the gas, and then divide the given mass by the calculated number of moles. And what you get is the molar mass.